In this video, we're going to look at quadratic approximation. So if you create yourself a linear approximation for cos of x near x equals 0, a linear approximation near x equals 0 would give you a linear approximation looking like this around this region here. You see, if you have cos of x, a linear approximation around this region here would be good, because a straight line here would be more appropriate for this region here, because a straight line here would be a good fit for this bit here. A straight line would be good, but a straight line here would not be good. A better one would be to use a quadratic approximation for this region here. Okay, so the idea behind a quadratic approximation is that you have to somehow come up with an equation for a quadratic, so that would be a good fit for near x equals 0. So around this region here, it would be a good fit. So the idea behind a quadratic approximation is for you to come up with an equation for this quadratic here, so that around this region here, it would be a good fit for this red line here, for whatever function this may be. Okay, so hang on. So the idea behind a quadratic approximation is that if you have a complicated function, let's just say a complicated function looking something like this. Okay, the idea here is for you to somehow come up with an equation for the quadratic, for the quadratic, such that it would be a good approximation around this region here. Okay, so or it may be something like this. Hang on. You see, we don't know what this quadratic may look like. It could be a negative quadratic, or it could be a positive quadratic. But the idea is for you to come up with a quadratic in such a way that around this region here, it would be a good approximation to the original complicated function. Okay, so the way we do this is to start out with our equation of our quadratic. So start out with the equation of our quadratic. Okay, so this is our quadratic approximation here. Quadratic approximation. Start out with our general quadratic equation here. Now, you want so this is our original quadratic here. You want to somehow find values of a, b, and c, so that originally that the original quadratic should equal this. Okay. And then the trick here, so I'm not explaining this very well, bear with me. Start with your quadratic. We don't know what this quadratic is. We just know that it's going to be in the form of this. We just know it's going to be in the form of ax squared plus bx plus c. Now the trick here is to differentiate this. The trick is to look at this quadratic here, and then differentiate it so that the gradient of our quadratic here will be the same as the gradient of this, and then work out the second gradient, or the second derivative of our quadratic, and make sure that's the same as the second derivative of the original complicated function around this region. You see what I mean later on. So start out with your quadratic here. So that should be the same as the original function. Well, normally what goes here is a complicated function, but because this is just an example, then normally this is very complicated. So start out with your normal quadratic here. This here should match up with this one here. Now the trick here is to get it so that looking at the derivative of our quadratic approximation, the derivative should be the same as the derivative of this. Okay, and then looking at the second derivative, make sure the second derivative of our quadratic will be the same as the second derivative of this. So the trick here, the trick is that you get given a complicated function like this. Your aim is to find out the equation of this quadratic here in such a way that it will be the best fit for this. Okay, and the trick here, the trick in doing this is to look at this region here. Looking at this region here, make sure that the derivative of this matches up with the derivative of this, and then make sure the second derivative of this matches up with the second derivative of this around this region here. Okay, so bear with me. So here you start out with your original quadratic here, and then this is our original function. Normally this is complicated, and then look at this, the derivative of this. Make sure that the derivative of this matches up with the derivative of this. So make sure that this will be the same as this, and then look at the second derivative of this, which is this. Make sure that this matches up with the second derivative of this, which is this here. So hang on. This is our original this is our original function. Well, if you put 0 into here, make sure that looking at the normal function, not the derivative, looking at the normal, make sure the normal of the black line here is the same as the normal of this purple line. And then the second part is make sure the derivative of this black line here matches up with the derivative of this purple line here, and so on. So hang on. So make sure the original is the same. So now we started out with this. Make sure that this will be the same as this at x equals 0. So we've got to put 0 into here, and then put 0 into here, and make sure these two will be the same. Remember, our aim here is to find out A, B, and C. Once we've got our A, B, and C, then this here will be a good approximation to this. Okay. So anyway, we are currently here at the moment. So now put 0 into here, and put 0 into here, and make sure these two are the same. Okay, so let's put 0 into here and 0 into here. That will then give you this. Okay, so looking at this here, if you put 0 into here, then this bit here will be 0. This bit here will be 0. So this here will just leave you C. Now if you put 0 into here, cos of 0 will be 1. So you can see that C here is actually 1. So really, in a way, we've found our C. C here is 1. Well, anyway, once you're here, put 0 into here, put 0 into here. That will then take you to this. Okay. So remember, this has to be the same as this. And then looking at the second derivative, put 0 into here, and then put 0 into here. Make sure that this will be the same as this. Okay. Well, if you put 0 into here, you will get this. You would just get B, because because if you put 0 into here, then this term here goes because of this x here. That would just leave you B. Okay. And then if you put 0 into here, minus sign of 0, that will be that will be 0 here. So make sure this is the same as this. So in a way, B is really 0 here. Okay, and then looking at our second derivative here. Now put 0 into here. If you put 0 into here, this side would be 2a. Okay, that's this 2a here. And then put 0 into here. This here will be minus 1. So make sure that this is the same as this. And so here a will be well here you've got 2a equals minus 1. So A will be minus a half. So basically, here we found C, we found B. B, by the way, happens to be 0. Okay, it happens to be 0 because you've got to get this to be the same as this. So really, B is this has to be the same as this, which is 0 here. This has to be the same as this. So meaning C is 1. This has to be the same as this. So 2a equals minus 1. So therefore A equals minus a half. Okay, so basically we've got our A, B, and C. B, by the way, is 0. So going back to our original quadratic here, our quadratic approximation, looking at this, don't forget B is 0 here. So this term goes. A is negative a half. So if you put negative a half in there, it will give you it will give you this. Okay, and then C is 1. That's this one here. C is 1. Remember, up here, C is 1. So overall, our quadratic approximation is given by this. Now, if you get a graph plotter, plot the original cos of x. That's the red line here, and this here is our quadratic approximation. And then you can see you can see that it is a pretty good approximation around here. Okay, and you could extend this to a cubic approximation as well if you wanted to. So with a cubic approximation, I don't know, you somehow have to approximate it. You have to create yourself a cubic here, or maybe it might look like a negative cubic, something like this. But the process will be the same. So you start out with your cubic here, but don't worry about the cubic because it's not very useful. It's only linear and quadratic that are useful. Cubics are just too complicated. But the idea will be the same. So start out with your cubic here. So start out with this, and the trick here is to make sure the derivative of the black line will be the same as the derivative of the red line, and then the next step is to make sure the second derivative of the black line will be the same as the second derivative of the red line, and then make sure the third derivative around here, the third derivative of the black line will be the same as the third derivative of the red line, and then slowly you eventually find your A, B, C, and D, and then that would give you your cubic approximation. But don't worry about the cubic approximation. It turns out to be not so useful because it's just too complicated. The whole point of us creating an approximation is to simplify things. This cubic thing is just too complicated. Okay, but roughly speaking, this if you really want to do a cubic approximation, I've only done it partially, so you have to finish the rest. But the idea will always be the same. You start out with your original cubic here, and then somehow and then look at the second look at the derivative of the first derivative. Make sure that the first derivative of the black line is the same as the first derivative of the red line, and then make sure the second derivative of the black line is the same as the second derivative of the red line, and so on. Okay, that's a trick. In the next video, I will give you some practice.